Today we're going to look at even and odd functions, and we're going to look at proving them algebraically. So in the previous video, we talked about proving if a function is even, odd, or neither graphically. Today we're going to look at it algebraically. The rule still applies that if it's an odd function, if I have f of my negative x value, I will get the negative f of x value. And if it's even, if I plug in a negative x value, I'll get the same f of x value. So let's do an example. Of course, I'm going to show you two different ways. This is the preferred method. So I have g of x equals x cubed minus 9. So I'm going to plug in a negative x. So instead of x cubed, I'm going to have negative x cubed. And I have a negative x. And I want to see what the new sign will be. So let's evaluate. X cubed, negative x cubed is still going to be negative x. And then a negative times a negative is a positive. And so if I look at this compared to this one, all of my signs are different. So here I have a negative, here I have a positive. Here I have a negative, here I have a positive. So this means that g of x, g of negative x is the negative of g of x, because all the signs change, and that's what it means when I change the signs. So this means that this is an odd function. Let's do another one. All right, so I have h of x equals x squared plus 1. Again, I'm going to plug in a negative x. And I'm just trying to see what my signs do. So that's a negative x squared plus 1. We know when we square a negative number, it comes out positive. So that's going to stay x squared plus 1. Notice my signs are exactly the same. So that means that my h of negative x is equal to my h of x. It's the exact same equation all over again. So that means that this is even. All right, here's another one. Again, I'm going to plug in my negative x. So when I evaluate, when I cube a negative number, it turns negative. All right, so this time my signs are not. So here I have a positive and a negative, and this is still minus minus. So this is totally different. So it's not the opposite, and it's not the same, so this is neither. All right, another one. Again, I'm going to plug in my negative x. All right. Well, this one is more difficult to evaluate because depending on what this value is, it's going to determine what happens on the outside. Because remember, when I take the absolute value tells me distance. So that means that distance is always positive because I can't ever go negative miles down the street. So when I'm talking about distance, I have to always come out with a positive answer. However, depending on what this value is, it's going to sway my answer. So it's going to make it change depending on what it is. So if I actually, like plugging in a negative x is probably not the best example to use because my answer is going to change based on that. So let's choose another number instead. Let's say x equals, let's say 2 instead. So if I plug in x equals 2, I get the absolute value of 2 plus 4, which is 6. All right, let's plug in x equals negative 2 instead. I get negative 2 plus 4, and the absolute value of that is 2. So these numbers are totally different from each other. So that means that this function is neither. They're not the opposite of each other. They are totally different. All right, here's another one. Plugging in a negative x. And I'm going to evaluate to see what happens to my signs. So I get negative x times the square root of negative x squared is just x squared minus 1. So notice these two equations are the exact same, except one is positive and one is negative. So when that happens, I know that it is odd. All right, so I am going to admit, most students do not like that method that I just showed you of plugging in a value to see if it's even or odd. Most students prefer the method that I'm going to show you next. So this is actually a trick, and it does not always work. It only works for polynomials, okay? This method does not always work. So for example, it won't work with my absolute value equations. It won't work with my square root equations. So this only works for polynomials. So algebraically, if all the exponents of the variables are even, then my function is even. If all of my functions, if all the exponents of my variable are odd, then it is odd. If there's a mixture of even and odd, then it's neither. Okay, so let's do some examples of this. So here I have an example. I have x cubed, my 3, this is my exponent, that's odd. 2 is the next exponent. Well, 2 we know is even. I'm just going to put an E there for even. Here I have x, so we know really this is x to the 1. There's an invisible 1 right there. And 1 is an odd number. And then here I don't have an exponent at all. But really and truly I do, because there's an x to the 0 power here. Okay? So whenever I have a polynomial, every last one of them has an exponent next to it, or an exponent that I can associate with it. So there's an invisible x to the 0. And when I raise anything to the 0 power, it's always equal to 1. That is a mathematical definition. Okay? So whenever I raise anything to the 0 power, it's always equal to 1. So 2 times 1 is still 2. So it's going to give me that 2 still back. And 0, I know this is also something new, is considered even. So notice I have an odd, even, and odd, and even. So this is a mixture of things. So this is definitely neither. All right, here's another one. Here, exponent is 2, so this is even. Here, exponent is 0, so this is even, 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 so this is an even function. Next one, even exponent, 4 is even, 2 is an even exponent, and 0 is an even exponent, so this is even. Let's go back. So again, here I have an odd and another odd. So this is odd. And this is what we got when we actually substituted our negative x in as well. Here I have an even and another even. So this function is even. And that's the exact same thing I got here. Here I have an odd and an even. So there's a mixture, so it is neither. Can't do it with this one, and I can't do it with this one. So I hope that this helps.